Hi there. In the last video, we had a look at finding the position of a particular term in an arithmetic progression or sequence. In this video, we're going to do a very similar thing, but this time look at a geometric progression. You can see that we've got a sequence here, 3, 12, 48, and so on. If you have a look at the difference between each term, it's not the same, but if I multiply 3 by 4, I get 12, and if I multiply 12 by 4, I get 48, and so on. So we have a common ratio, and therefore it's a geometric progression. And just like the other video, you can see there's a slightly harder problem to do over here, and it will be tackled in a very similar way to the arithmetic progression. But because it's a geometric progression, it does look quite a bit different in terms of the execution. So the idea is the same, but the execution is different. So just to remind you that the formula for a geometric progression, the nth term is given by multiplying the first term by the common ratio raised to the power of n minus 1. So if it was the fifth term, that'd be a1 times r to the power of 4, 5 minus 1, etc. So let's have a look at it in relation to this problem here. We're asked to find out which term is 49,152. So we use a very similar process to start with, in that we use the general formula there, an equals a1 plus r to the power of n minus 1, and we substitute the stuff we know. So we know that the term we're looking for is 49,152. So I put 49,152 down, and then I set it equal to the first term, which we know is 3, multiplied by r, which we don't know, and n minus, we do know r, let's take that back, multiplied by r, which is 4, raised to the power of n minus 1, which we don't know what n is, so therefore we don't know what n minus 1 is. And now we solve it. We cannot get to the n while it's raised to the power of 4, and we cannot get to this term while it's multiplied by 3. So the first thing we have to do is divide both sides by 3. Now this is likely to be a calculator operation unless you can be bothered doing the short division. I've done this problem beforehand, so I know the numbers, but there's no dramas with using a calculator if you so wish. So when you divide 49,152 by 3, you get 16,384. So that's what 4 to the power of n minus 1 is. Now, we have dealt with problems where the variable is raised to a power, like x to the power of 7, and we know that we take the 7th root of both sides. That's no dramas. But what do we do when there's a power the unknown is in the power itself? And the answer is, you're not going to like the answer too much. To be perfectly honest, the calculation-y way of doing it at this stage would require a new function called logarithms. And we haven't done logarithms in Year 9. In fact, you don't do it until Maths Methods Foundation, which is a Year 11 subject, or you'll do it in Maths Extended next year in Year 10. So what do we do instead? Well, we basically whip out our calculators and we start going 4 to the power of until we get the answer that was 16,384. So you would go, what's 4 to the power of, I'm going to do it off to the side here on my own computer, so you won't be able to see it on the screen, but I might go have a guess and say, what do you think it might be? Maybe pause the video and think about, what do you think, 4 to the power of what do you think will get you to 16,384? 4 to the power of 10? 4 to the power of 11? What? Okay, so let's start with 4 to the power of 10. Whoa, 1,048,000, so that's way too high. So we'll try again. Let's go 4 to the power of 4. Well, that's way too low, 256. Sorry you can't see this, but I'm just calling up the numbers hoping you're okay with it. What about 4 to the power of 6? 4,096. That's looking better. 4 to the power of 8? 65,536. That doesn't work. 4 to the power of 7? Aha, that's exactly equal to 16,384. Okay, which is our number. So we can say that the power, not n, but the power, which is n minus 1, must be equal to 7. Okay, and just for the notes, which I'll give you as well, I'll just say this was done by trial and error then. Trial and error approach, and therefore n equals 8. And if you want to, you can finish with i.e. the 8th term. Now, it's a bit tedious, I know, and like I said, in grade 10 Maths Extended or Maths Methods Foundation in grade 11, you would learn a process called logarithms, or a function called logarithms, which would allow you to get that answer directly instead of having to do trial and error. But until then, as long as you can make some decent educated guesses, it's just a matter of putting in a value and then adjusting until you get it right. Okay, so let's have a look at the slightly harder problem. Same sequence, but when does the sequence breach go over? In other words, 1 million. And we're assuming that the sequence won't actually hit 1 million, but it'll be either side of 1 million between one term and another, just like we did with the arithmetic progression and 0. We start off the same way. We use our general formula, an equals a1 plus r to the power of n minus 1. We substitute the values we know. And again, just like in the arithmetic progression, even though we think that 1 million isn't actually a number, it'll tell us where the position will be. So we put in 1 million for an, we put in 3 for a1, we put in 4 for r, and raise it to the power of n minus 1. Now the process remains the same as we did for the example above. We divide both sides by 3, and we get 333,333, and because it's easy, I'll write it exactly, 0.3 recurring. That's what the dot above the 3 means, remember, is equal to 4 to the power of n minus 1. And then it's trial and error time again. So you can have a guess. You might remember from last time that 4 to the power of a 10 was 1,048,000. So we'll do the trial and error again. I'll put some notes here next to it so you can sort of see where we're coming from. It turns out that 4 to the power of 9 is equal to 262,144, and 4 to the power of 10 is equal to 1,048,576. Okay, so that's the trial and error bit. So what does that mean about 4 to the power of? It's going to be 4 to the power of 9 point something will give us 333,333. Okay, so we know that n minus 1. So watch what I'm doing here. We know that n minus 1 must be bigger than 9. That's good enough, I think. I don't have to work it out to a decimal place, and I can't really. I mean, I could try and error with my calculator and get n equal to 9.317 or something like that. Who knows? But I think just knowing it's between 9 and 10 is all we really need. And therefore, we can conclude that n must be bigger than 10. So when n is bigger than 10, we know that it's the sequence is going to hit over 1 million. So that's basically all we need to worry about. Because n is a whole number, because it's a counting number effectively, term 1, term 2, term 3, term 4, up to term 10, then I can say with confidence, i.e. the 11th term, the first term after the 10th term, is the first term to breach is the first term to breach 1 million. Now, what I did before the video is I actually calculated what the 10th term and the 11th term is, and this is what I got, just so you can sort of see it. A10, the 10th term, is 3 times 4 to the power of 9, that's 10 minus 1. That's actually 786,432. So you can see that by the 10th term, we haven't quite got to 1 million. And then A11, have a guess what that is. That would be 3 times 4 to the power of 10. And that's actually 3,145,728. So not only does it go over 1 million, it's massively, it's like 3 times 1 million. But nevertheless, the 10th term's not there yet. And this is a classic example of how geometric sequences or progressions are exponential in their growth. That is, between one term and the next, there's quite a significant amount of growth. So you get these sort of wild results like going from just under 1 million to 3 times 1 million just in one step. Okay, I'll leave the video there. Hopefully that's been helpful to you.